Okay, let's continue on to crustal deformation. So we saw before that horizontal sedimentary rocks are deposited in horizontal layers, but these horizontal layers can subsequently be tilted and deformed by tectonic forces into such things as folds, which are twists or bends in a rock, joints, fractures in a rock, and faults where rocks on one side of the dislocation are displaced relative to rocks on the other side. There's a branch of geology called structural geology involved with the study of the architecture and processes responsible for deformation of Earth's crust. It's very important to have a working knowledge of rock structures as applied to a modern way of life. For example, if for major construction projects like, for example, building a dam, it's important to know whether the surrounding bedrock is riddled with faults or whether it's very strong and massive. Also for construction of buildings, particularly skyscrapers, things of that nature, it's important to understand the structure of the underlying bedrock. So too in the case of oil and gas reservoirs, where these economic accumulations tend to occur within anticlines or against faults, things of that nature, as well as hydrothermal ore deposits, which oftentimes occur within fracture systems in pre-existing rock. Deformation is a general term that refers to all changes in the original form and or size of a rock body. And as we would expect, most crustal deformation occurs along plate margins where lithospheric plates interact with one another. We saw before differential stress is where stress is applied unequally in different directions. By definition, stress is simply force applied to a given area. There are three types of differential stress. There's compressional stress, which acts to squeeze and shorten the body. Tensional stress works just the opposite. It stretches the body and pulls it apart. And finally, we have shearing stress, which pushes different parts of the body in opposite directions. So let's start with an illustration of undeformed strata, basically a rock body, and compare that with a cube of rock that's going to undergo the same types of differential stress. Now, in the case of horizontal compressional stress causes rock bodies to shorten horizontally and to thicken vertically. The result is that there's oftentimes crustal uplift in mountain building associated with this type of stress. On the other hand, horizontal tensional stress causes rock bodies to lengthen horizontally and to thin vertically, resulting in entirely different structures on the surface, that of horst blocks interspersed by valleys termed grabens. And we're going to look at horst and graben structures in a little bit more detail when we consider normal faults. Shear stress causes displacements along fault zones or by ductile flow, but in general there's really no significant uplift associated with two crustal blocks sliding horizontally past one another. Now, strain, by definition, refers to changes in the shape or size of a rock body caused by stress. And as a result, rocks subjected to stresses greater than their own strength typically deform by either folding, flowing, or by fracturing. Now, the general characteristics of rock deformation include elastic deformation. In this case, the rock body returns to nearly its original size and shape when the stress is removed. A good example of elastic deformation is simply a rubber band. You take a rubber band and stretch it apart and release it. The rubber band springs back to its original shape and size. The same thing with a rubber ball. When you squeeze the ball and release it, the ball springs back to its original size and shape. Those are good examples of elastic deformation. On the other hand, once the elastic limit or strength of a rock is surpassed, then it either fractures in the case of brittle deformation, or flows in the case of ductile deformation. There's not a whole lot of elastic deformation to rocks. Ultimately, rocks deform permanently as a result of the stresses exceeding the overall strength of the rock. Now, brittle deformation can be compared with ductile deformation. Brittle deformation results when increases in stress causes the rock to deform mainly by fracturing. And this type of deformation is typical of the upper crust, where lower temperatures and pressures, particularly confining pressures, prevail. On the other hand, in the case of ductile deformation, increasing stress causes the rock to undergo smooth and continuous deformation. The rock, in turn, will then contort and change shape without fracturing. This type of deformation is typical of the deep crust, characterized by high temperatures and high confining pressures. And we see both examples of brittle and ductile deformation in that photograph to the right. And here's another example of ductile deformation. The original rock was horizontally layered, but has since been contorted into folds as a result of compressional stress under very high temperature, high confining pressure situations. We saw before that confining pressure results from the weight of the overlying rock pushing downward and from all sides. And it's like the pressure that we feel when diving deep underwater, where stresses push against the body equally in all directions, and the rock, as a result, is squeezed from all sides. The result of confining pressure is that the rock simply decreases in volume within deeper parts of the sedimentary basin. On the other hand, the stresses, as shown by these arrows, are equal in all directions. Confining pressure is an important factor in determining how rocks deform. In general, brittle deformation is more likely at shallower depths and lower confining pressures. And under these conditions, rocks deform mainly by fracturing and faulting. On the other hand, ductile deformation more likely occurs at greater depths and higher confining pressures, where rocks flow and contort, deforming without fracturing. Another factor that determines how rocks deform is temperature. In general, brittle deformation occurs at lower temperatures and ductile deformation at higher temperatures. A third factor is the rock type. Rock salt, for example, is susceptible to ductile deformation, whereas granite will more likely fracture. Also, igneous and metamorphic rocks are stronger and tend to resist deformation to a greater extent than do sedimentary rocks. And finally, time. The longer the stress is applied, the more likely the rock will deform, and also the greater the deformation. I like to illustrate time by considering a bookshelf. And when you first buy a bookshelf and you put books on the shelf sustains those books. But over time, even when you don't change the number of books on the shelf, you'll notice that the shelf will gradually begin to sag. And over time, it'll sag more and more. This is a good example of how increasing time will cause the shelf, or in this case, the rock, to further deform, even when we're not changing the overall stress that's applied to the object. So in summary, crustal depth and the type of stress that's exerted in large part determines the overall type of rock deformation. And we see this example in this figure. At shallower crustal depths and lower temperatures, rocks will typically exhibit brittle deformation. The type of brittle deformation depends on the stress that's exerted. At greater depths, on the other hand, rocks will deform by ductile flow, where we more likely get folding and stretching and shearing of the rock body. Okay? Now, geologists prefer to measure rock deformation using units of strike and dip. Now, the orientation of rock layers, folds, fractures, faults, these can all be measured in 3-dimension using strike and dip. Strike, by definition, is the direction of a line formed by the intersection of a rock layer with an imaginary horizontal plane. Here, for an example, we have a series of dipping strata, and as we pass the horizontal plane through the rocks, a line of intersection is defined on the rock, and this is the strike direction. The line of strike can be defined as a compass direction, as, for example, due north-south, north 30 degrees east, or east-west. And what's more, we can represent strike on the symbol as the longer of the two lines represented in this particular figure. So the longer line is the strike line, and that can be given the strike or a compass direction on the map. Does everybody understand what the strike is? Does anybody care? Okay. The dip, on the other hand, is always measured at right angles, 90 degrees to the strike, and is a measure of the angle at which the rock layer tilts relative to that horizontal plane. So in this case, on the strike dip symbol, the shorter of the two lines is oriented at 90 degrees to the strike and points in the direction of dip. In this case, the dip angle of the strata is 30 degrees, and we indicate that by writing 30 degrees next to the dip. And that gives us the strike dip of this particular sequence. Yeah. The dip can be also thought of as the water line, just the direction that the water will flow if from this leaky canteen. And it's always going to be at 90 degrees to the strike. The dip is always an acute angle. The dip is always less than 90 degrees. We can also measure an angle of dip in the other direction, but that angle would be greater than 90 degrees. So we always take the direction where the dip makes an acute angle less than 90 degrees with the horizontal layer. In this case, the dip is to the right. Now here's a photograph of two people walking along a ridge of exposed dipping strata. Now, are these two children walking in the direction of strike or dip? Yeah. They're walking right along the strike direction. This ground surface can be thought of as the horizontal plane that intersects the dipping strata, and that line of intersection indicates the orientation of the strata. These dipping layers are strata that are more resistant to erosion, so they tend to stick out. There's also a strata in between, but these are softer shale layers that have been eroded down. Which is the dip direction, to the left or to the right? To the left, yeah. And what's more, we can measure the angle of that dip. The strike and dip of rocks is measured using an instrument called a Brunton compass. And that Brunton compass is in fact a compass, but it also has other features, particularly these little tubes with bubbles that are used, for example, to level boards or things like that when you're in construction. But anyway, this Brunton compass is taken into the field by structural geologists, and the strike and dip of strata that are exposed on the surface can then be directly measured in the field. If I think about it, I'll bring one to class and pass it around. Now, here's a map view of the block diagram shown below. The map view is the surface view of the block diagram, and the cutaway view is the cross-section showing what the rock layers are doing underneath. Above, we have a representation of the map view, which is called the geologic map. And on this geologic map, we have strike dip symbols. So let's look at this in a little bit more detail. Notice, first of all, that the longer strike lines tend to parallel the contacts between adjacent rock layers. Here, for an example, is the contact between the sandstone and the limestone in map view, and that contact is always represented parallel to the strike direction. The shorter dip lines are always oriented at 90 degrees to the strike. And what's more, the dip angles are indicated next to the strike dip symbols. So in this case here, these beds in cross-section are dipping at 30 degrees to the left. Notice that this strike dip symbol is pointing to the left. This strike dip symbol is pointing to the right and indicates an angle of 85 degrees. That's representing this particular dip, where the dip is at 85 degrees to the horizontal. And then over here we get a reversal back to the left in terms of dipped, and that represents this particular sequence in the cross section. So we'll come back to this in a little bit, but let's move on to folds. Folds result from ductile deformation of rocks in response to mainly compressional stress. Anticlines are layered rocks that are folded into arches, whereas synclines are layered rocks that are folded into troughs. And notice that the anticlines are interspersed with synclines in the overall folded terrains. Here, for an example, is an exposure of folded limestone where the anticline is to the left and the syncline is to the right. And here's another mountainous slope showing the overall form of an anticline. Here's a schematic representation of a block diagram. In this case, we have a anticline, and in the foreground, we have a cutaway view showing the orientation of the rocks within this particular structure. And in here, we see the line of strike and on both sides, and the line of strikes in turn parallel the longer of the two lines in the strike dip symbols. To the left, the straight up is dipping towards the left at an angle of 20 degrees. We see this in a cross section. To the right, the straight is dipping at an angle of 60 degrees to the right, and that's shown by this strike dip symbol. Yeah. Now we can look at an overall fold, in this case an anticline, and break it down into different structural components. Now the two sides of a fold are referred to as the limbs. And notice that opposite limbs come together along an imaginary line that's called the hinge line. And what's more, that hinge line defines the overall strike of the fold. So we can define the fold strike as a compass direction, maybe north-south, north 30 degrees east, or whatever. And we also have an vertical imaginary plane called the axial plane that divides the fold into two symmetrical halves. So that if you look at the cross-section of the cutaway view of the figure, the left side of the cross-section is the mirror image of the right side. And here we see these different features associated with a fold. We see the hinge line in the upper figure, the axial plane that passes vertically through the fold. And notice that when we erode away the upper part of the fold, the limbs appear as two horizontal ridges on both sides of the axial plane. And what's more, the intersection of the axial plane with the ground surface defines the hinge line, which is also the strike direction of the fold. So several things are going on here. Is there any question about any of these features? We can put these same things on in synclines. Synclines can also have an axial plane, a hinge line, and limbs.
Are they going to be symmetrical?
They can be symmetrical too, yeah. But not in all cases. We can have asymmetrical folds, which we'll look at in more detail next time. Now here's this is a cutaway view of a fold. In this perspective, the axial plane projects in and out of the screen, and we see that the limbs dip in opposite directions on both sides of the axial plane. In this case, this is a symmetrical fold. One side of the fold, the left side, is a mirror image of the right side. Now here's an interesting structure. This is what's known as a plunging anticline. We're going to look at plunging anticlines next time. But this large anticlinal feature has been eroded. And along the flanks, we have dipping strata that are dipping towards the left. These geologists call these hogbacks. And further over, we have sedimentary cover, which obscures the deeper portions of these folds. But a geologist can go walk right up to these hogbacks and with a Brunton compass can directly measure the strike and dip of the strata. And also, if you follow these hogbacks along this figure, notice in the background the strata bends around, and on the opposite side actually dips in the opposite direction. So this is a characteristic of a plunging fold, a plunging anticline that we're going to look at in more detail. But first of all, I just want to take you through the different steps in pointing out these various features of anticlines and synclines. And below we have a block diagram, and above we have a representation of the map view in what's called a geologic map. So let's start out with the surface of the block diagram, the map view, and the cross section, which is the cutaway view. And above that is the geologic map, which represents the rocks as they would appear on the surface if we stripped away all the vegetation and soil. And we see in the geologic map we have a red shale, a sandstone, a limestone, and we see these different rock units also in the cross section. Okay. Now we see in cross section that we have an anticline to the left, and to the right we have a syncline. We can therefore construct a hinge line of an anticline which goes over the limestone, and we can also construct a hinge line for the syncline which parallels the red shale. So we'll keep the hinge lines and get rid of all this other text and start by noticing that in the geologic map, in folds, in general, strata are duplicated on both sides of the hinge line. So, for example, each of those sandstone layers are the same sandstone formation. And we see these sandstone duplicated on both sides of the hinge line in both the anticline and the syncline, and so too the red shales and the limestones are also duplicated. This is a characteristic of folds when viewed from a geologic map. Now, notice that the strata dip away from the hinge line in anticlines. So on the strike dip symbols, also notice that the dip symbols dip in opposite directions. On the other hand, strata dip towards the hinge line in synclines, and as a result, the dip symbols point towards the synclinal hinge line. What's more, in anticlines, the oldest strata occurs right along the hinge line, in this case the limestone. We know that the limestone is the oldest because if we look at the cross-section of the three formations we're considering, the limestone occurs at the bottom, and the red shale is the youngest because it occurs at the top. So we see that in anticlines, that limestone is exposed right along the hinge line. And as a result, in anticlines, strata become younger as we move away in opposite directions from the hinge line of the anticline. On the other hand, in synclines, the youngest strata tends to occur right along the hinge line, and the strata become progressively older away from the hinge line in both directions. So whatever you learn for the anticline, simply reverse it for the syncline. Yeah. The hinge line is good for mapping folds on geologic maps. If you map the hinge line on the map, right away you can tell that these are folds, and you can also indicate the direction that the folds are striking. All this information can be derived from the map without having to look at a block diagram cross-section. These are various map symbols that show up on geologic maps. So here we have a block diagram of a syncline, but we can put in the same features. For example, we can construct a hinge line right through the center of the basin. That hinge line in turn defines the strike of the syncline. And we see that the youngest strata, in this case the gray shale, occurs right along the synclinal hinge line. And the strata become progressively older away from the hinge line. And again, we have a synclinal block diagram and the geologic map shown on the top with the hinge line, the purple or the blue arrow indicated. And again, notice that if you focus on the strike dip symbols, notice that the dip symbols on both sides of the hinge line point towards the hinge line, which is characteristic of synclines where the strata dip towards the hinge. Already. Any questions? This is a good place to quit. Okay. Well,